Hello, my name is Richter, and today I would like to talk about next generation sensor fusion for next generation sensors and driving functions. So why do we need a next generation sensor fusion? So first of all, we have seen that the current approaches that exist have some properties that limit their applicability for those next generation driving functions and also sensors. On the other side, we propose an integrated approach that resolves these limitations and thus enables next generation driving functions. So which kind of driving functions are we talking about? Of course, we have classical functions like emergency braking in mind, but this time we rather talk about urban and city scenarios. We have, on the other side, really automated driving functions like valet parking, and there's another group of driving functions like piloted driving or traffic jam pilot systems. Here I have a short video about an automated vehicle that is already on the road, and we see that something went wrong here and that this car hits that pole, and we will come back to that pole or that static object in a second. I have another interesting example here where we can see that not only static objects are of high interest, but also any kind of dynamic object is very interesting for any automated driving function. So what we have seen is that on the one side, as I already told, we need to distinguish between different types of static objects, but as we all know, there are also many different traffic participants or dynamic objects in the scenes that we need to support. Additionally, the number of scenarios that we need to support is increasing, and also their complexity increases over time, so it gets more challenging. And in general, we see that the level of automation is further increasing. So for those requirements, what kind of environmental model is required in order to support next generation driving functions? Of course, all kinds of dynamic objects, be it small objects or extended objects, all kinds of static objects, and free space, so the space where the vehicle can potentially drive to. On the sensor side, such an environmental model needs to support high-resolution sensors, and this is true for all the sensor modalities, be it radar, camera, or LiDAR. So how was that solved in the past and with current sensor fusion approaches? So what we see in the market, or what we often see in the market, is a combination of dynamic object fusion on the one side and a so-called static occupancy grid fusion on the other side. And this approach has some advantages, like it is well suited for higher distances, or for objects that are in larger distances. It's also well suited for highly structured environments where you know lots of things in advance. And of course, this approach is highly modular. You have two different fusion approaches, the dynamic object fusion and the static grid fusion, and they can be developed independently, which is an advantage by itself. Kind of a built-in property of these algorithms is that they have support for current generation sensors, which provide data at a low resolution. Despite the fact that these algorithms have some advantages, they also have limitations. And I would like to have a closer look on these limitations. Especially when it comes to small distances and objects that are extended, spatially extended, then especially dynamic object fusion has its strong limitations. Additionally, it requires that each object is known during design time of the system, and this introduces a risk that you miss objects that you haven't seen before or that you haven't had in mind when developing the system. Another property of these algorithms or of dynamic object fusion is that once you want to use that with high resolution sensors, then you need an extra step before the actual fusion, which I would like to call object extraction in this presentation. So you put in high resolution sensor data on the one side and you get out extracted objects from such an algorithm. And if this algorithm works well, then the whole approach works well. However, we have seen it many times that this object extraction step fails and extracts wrong properties from the objects, like you can see on the right side. And as soon as this happens, then you have a high risk that the whole sensor fusion system fails in challenging scenarios. Let's have a look at the other part of the current approaches, the static grid fusion. So on the right side, you see a typical representation of such a static grid fusion. It is a world that has been discretized into a number of discrete cells. And the main assumption of static grid fusion is that the whole environment is static. So, which means that there must be no dynamic object inside the environment. We all know that the real world contains dynamic traffic participants. And if you still use static grid fusion with dynamic objects in the scene, then this results in free space that is outdated, which is also often called the tails that we see in this approach. There is a workaround for that effect, and typically developers then say, well, let's exclude the measurements from the dynamic objects to circumvent this effect. But then again, the question arises, okay, but from where can we get the dynamic objects? Well, and very often then the answer is we take the dynamic objects from the dynamic object fusion and put them into the static grid fusion to exclude the measurements from dynamic objects. And I guess you can already see the effect that this has. Once the dynamic object fusion has an error due to the fact that the object extraction made an error, then this error propagates from the dynamic object fusion to the static grid fusion. And again, you have a high risk that the whole system fails in certain scenarios. All these limitations led to a new development, and we call this development and our approach dynamic grid fusion. Now let's have a look at the dynamic grid fusion in detail. I have a small video showing the dynamic grid fusion in action, and you can see this in the center of this video in the colored image. What you will see in a second is a car that moves around on the road and how this grid evolves over time. We have in green free space, we have in red all the static objects, and we have in blue all the objects that are moving or that are dynamic objects. We start the video at a parking lot, so we have a lot of free space around the ego vehicle, around the host vehicle. Now we enter a public road, and we can already see some dynamic objects like this cyclist, which is marked in blue here. Here we can see another typical situation, a crossing van, which is properly determined by the system. You can see how the heading value has been estimated by the system. On the left side, now you see a stopped car, and behind the host vehicle there is a moving car. Watch how its state changes from dynamic blue to stopped or static in red, and again back to blue to moving or dynamic in the scene. Fast forwarding the scene, here we can see another interesting thing. Here's a pole that could be the pole that we have seen in the first video where the car crashed into that pole. With such an algorithm, you would have seen that pole. Now we enter a roundabout. It's also very interesting to see all the other traffic participants, how their driving direction or the heading value is estimated. And we will leave the roundabout and go back on the straight road again. And then I have a last example before the video finishes. That is this bus here, which is a large extended object. And you can see how this object is properly determined by the algorithm. Let's have a closer look at the dynamic grid. In simple words, it's composed of two existing algorithms. On the one side, we have the static equivalency grid that is already in use in the market and in many cars, which can distinguish between free and occupied cells. On the other hand, we have another algorithm that is combined with the static grid fusion. That is some kind of particle filtering, which means that for each of the cells in the grid, we add a number of particles, and those particles, they are responsible for estimating the velocity of dynamic objects and their driving direction. Now you may wonder about the performance of such a system if we introduce particle filtering into the system. We did some tests on typical automotive CPUs, and we can tell that such a dynamic grid fusion runs in real time on typical automotive CPUs, or in other words, there is no GPU required for such an algorithm. In addition to the object dynamics, the dynamic grid can also process additional information, especially semantic information or semantics, like the object class of dynamic objects, whether it's a person, a car, or a truck. But it can also process information about free space to further classify that free space. And all this information further improves the robustness of the dynamic grid approach. So what are the actual benefits of the dynamic grid? On the one side, we have a high detection rate. And this is because of the low-level sensor fusion approach that does not rely on any object extraction. So errors that come into the sensor fusion by the object extraction can simply not occur. Second, we have a low false alarm rate because we do an integrated estimation of both static and dynamic objects. And last but not least, the last benefit is that such an algorithm can run on typical automotive CPUs, and we can do this by minimizing particles in static areas. Key takeaways from my presentation. Once again, we saw that current sensor fusion approaches have some properties that limit their usage for next generation driving functions. Second, integrated sensor fusion approaches like the dynamic grid resolve these limitations. And the dynamic grid can be executed on CPUs and It's already available today. Thank you for your attention.